Hi, my name is Stephen. I'll be talking briefly about experiments at Sony Interactive Entertainment with using Dexter to tune an optimization pipeline for OG and give some of our results. OG is an optimization option in GCC intended to give performant code without compromising debug info. This is necessary for debugging applications that require optimization due to speed or space constraints. Clang has an OG option for compatibility reasons, but right now it is the same as O1, and previous discussions about it have been hampered by the lack of usable metrics for debug info quality. We have created such a metric by measuring the availability of variables and breakpoint locations. This is accomplished by using Dexter, a debugging integration test tool in LLVM, to record the debugger output for a hand-selected set of variables and source lines in an internal codebase. From these recordings, we produce a debuggability score equal to the sum, for all variables, of steps where that variable's value was correct. Debuggability is only one half of the equation, though, as it is a trade-off against performance, which we measured for each pipeline using an already existing benchmark. With these metrics, we tested a set of candidate OG optimization pipelines to see what effect they had on debuggability and performance. This graph shows debuggability versus performance for the existing speed-optimizing pipelines, with performance given as a multiplier of the O0 score. So a score of 2 for a pipeline means the compiled benchmark completed twice as fast for the same benchmark compiled with O0, also plotted as a provisional OG pipeline that we selected from our experiments. As you can see, our provisional OG compared to O1 has a 4.8% performance cost for a 27.3% debuggability gain, which is a reasonable trade-off. Now I'll talk quickly about how we selected our candidate pipelines. Similar to GCC, our approach was to start with O1 and disable the passes that are bad for debug info. However, we have to contend with the phase ordering problem. Running one pass may affect the output of subsequent passes, so we can't just test disabling each pass individually, but we have to test combinations. Unfortunately, the Dexter tests are not fast enough to explore every combination and ordering of passes. And there are a few established methods to deal with this problem, but for our prototype, we simply simplified the design space. We grouped sets of passes together, generally those that were adjacent and either performed similar transformations or were intended to directly capitalize on each other. These groupings are intended to be meaningful, but only as a starting point for further investigation. Some blocks are broader than would be ideal, and some contain quite a mixture of passes, but they are useful as a broad overview to guide the next round of tests, having provided some insights that I'll briefly talk about as we go through to the results. For the first point of the results, though, I need to talk about the extend variable lifetimes flag. This is a flag that we've created and is currently under review, which inserts fake uses of local variables and parameters to extend their lifetimes through optimizations. In the debuggability versus performance graph shown, that top left point is current O1, and the cluster of points in the bottom right are a set of pipelines that we tested with extend lifetimes enabled, including O1. As you can see, there is quite a gap. That flag alone improved debuggability by 22.1% for just a 2.4% performance cost. This is very significant, but we still need to look into the opportunities offered by pass selection. So for clarity, we'll focus in on the results that used extended lifetimes. On the whole, there are few free wins. Many of the tested pipelines have poor trade-offs of debuggability for performance, and some even made debuggability worse. Labeled here are the optimal results for any linear trade-off of performance and debuggability. Although we can't infer too much from this first round of results, there are a few interesting trends. Some passes gave small debuggability improvements for almost no cost, but only when disabled by themselves. For the basic simplification passes early in the pipeline, disabling some generally gave a strong improvement, but disabling all simplifications of the same type gave a lower score. Inlining and loop vectorizing appear to be the most important sets of passes by quite a margin, and so are key candidates for any OG pipeline. But with that in mind, the OG pipeline selected for our candidate is the one with the highest debuggability, which removes loop simplifications and loop vectorizing. The overall performance trade-off there is still strong. So to summarize where we go from here, the results shown so far are not final by any means. We'll continue to narrow down our search to find the passes that give us the best trade-offs to iteratively improve OG. Furthermore, while all the benchmarks we tested here are non-public, there is potential for an open source benchmark to be created, allowing us to publicly track and verify debug info quality across versions. Furthermore, from a development point of view, these tests show the value of the extend lifetimes flag. Please review it if you get the chance. It is good encouragement for other debug enhancing flags to be written. And finally, Dexter's detailed reporting across a large code base gives us another tool to identify debug info regressions and areas for improvement throughout LLVM. Thank you for listening. If you have questions, come and talk to me later.